So let's get started. It's a great pleasure. I'm bringing back Steve Morris. He was here in 2014, so four years ago, and he was talking about ornithopters then, and it's kind of interesting that he keeps revving them and they keep getting better and better. And the thing that caught my interest 4 years later is he's starting to talk about thermaling with his ornithopters, and that's when we get really excited. So I thought it was time for an update, and so let's give an applause for Steve and let him.
Can we start the slides?
Yeah, we'll start the slides here.
I see it just great.
Okay, so you see the slides, okay?
All right.
Yes, sir. Yes, thank you.
So I'm going to be talking about radio-controlled ornithopters, which are airplanes that flap their wings to fly. And the title says, a bunch of bigger words, says passively deforming aeroelastic wings. And that's a fancy way of saying a wing that automatically deforms under load to hopefully capture the correct shape for efficiency. So in other words, we're not building a wing where you have to put a whole bunch of servos or motors or something in the wing to make it have the right shape to fly well. We're designing the structure and the mass and the shape of the wing so that if you just move it up and down, hopefully this thing will fly right because the wing automatically changes shape. That's more along the lines of the way that I think birds operate, and this whole thing I'm talking about has just been a long, ongoing experiment to test that theory. And the goal has been to not only make an ornithopter that flies efficiently, but that can also glide well. Because there are a lot of model ornithopters. You can go to the store right now and buy a little toy ornithopter that looks kind of like an insect when it flaps. And it'll fly nicely. But as soon as you stop the motor, if you can lock the wings, it has an L/D of maybe 2 to 1, 4 to 1. It just hits the dirt. It does not glide. Well, my models are trying to be more bird-like. Next slide. So, obviously, flapping flight has been invented by nature many times over in birds, reptiles, and in mammals that have all evolved the ability to fly. Somewhat different mechanisms are used, but there's a lot of commonality in bone structure and the way the wings work. Even though a bat has a membrane wing and bird has feathers, there's still commonality in how the wings move. But it's been, for millions of years, animals have known, nature has evolved the ability to fly. And to do it really well compared to what man has been able to achieve. My second bullet point there says humans have failed to duplicate this efficiency. You can see, we're seeing some of my friends watching this.
Turn off your video camera.
Wait, do we need them to turn off theirs?
Yeah.
Oh, hey Alex, I think your video is coming through on ours right now. You may have to turn it off.
Okay, that looks good.
Yeah, we're good. So, what I'm getting at here is that this is sort of the kind of an embarrassment to engineers. Here we are, well over 100 years since the Wright brothers first flew. We've got all these supercomputers. Everybody thinks we know everything about airplanes and how to make them fly. Nobody has built an ornithopter that has come remotely close to the overall efficiencies that birds regularly demonstrate. And it's because it's a difficult problem, and a lot of people just haven't analyzed it properly. You could take, you're all familiar, you build some of the most efficient model airplanes. You're building soaring aircraft. L/D's probably approaching 20 to 1, maybe more for some of the better ones. You could put a small motor on some of your sailplanes and sustain very easily. You could put solar cells on it and fly all day and through the night charging batteries. But if you built that same model with flapping wings, if you didn't do it right, it would be 4 or 5 times less efficient because we just don't know how to build the wings to maintain the shape to achieve that. And so when you look at all the airplanes, the ornithopters that have been built, they're usually consuming at least double the power in level flight than the same size airplane with a propeller on the front. And the propellers are only 60 to 80% efficient. One of the arguments for flapping flight is that the wings act on so much air that the efficiency should be very high. Well, we know how to build propellers above 80% efficiency if you're willing to carry a big propeller on the front. Human-powered airplanes have that. A lot of just regular old airplanes that you might get in at the airport have propellers in the 80+% efficiency range. So why do we need to go to the trouble of flapping wings? I mean, it's a lot of engineering challenge there. Well, we should at least understand what nature has figured out, because those solutions might apply somewhere else. That's one reason to study this. So how do we design an efficient flapping aircraft that can also soar? Next slide. On the left is a kind of the typical radio-controlled ornithopter. That airplane is called a Park Hawk. It used to be in production. Sadly, the inventor of that airplane died a few years ago in a car accident. He's kind of famous in the ornithopter community, Sean Kincaid. He designed that aircraft, and it was really the only radio-controlled ornithopter you could buy for many years before the small toy-sized ones came about. It's a very simple design. The wings flap up and down. They're made of Dacron, and they have a couple of battens in them. When the wings are not flapping, they're perfectly flat, just membranes. And the glide ratio of that thing is barely 5 to 1. On the right, you see an eagle and a seagull. You're just to show birds just doing what they do every day, doing very well. Unfortunately, the models are often at a disadvantage because they just use these membrane wings. They don't have real airfoils. They don't even have defined camber. The twist of the wing in gliding flight, if you could see a Park Hawk type model flying, it would have ridiculous amounts of washout in gliding flight. So it doesn't even have a good span-wise twist distribution. So they suffer greatly in glide performance. Birds, on the other hand, are extremely aerodynamic in all flight modes. The feathers on a bird wing allow it to change span, area. You could change the wings asymmetrically. The dihedral, they have muscles that allow the feathers to pull downward and camber the wings in flight. They can do all of this, and they don't have like a big protruding struts or servos sticking out of their wings. It's all aerodynamically fared in. The muscles of the body are all contoured with feathers. So they're highly evolved to be efficient, and yet they can not only can they soar and flap their wings and fly, but they can land and fold their wings into a compact form. They can swim, they can dive underwater. They're just amazing at what they can do. So we're way behind on that. Let's go next slide. Here's some of the better examples of what engineers have done. So on the left side, in the bigger picture, that is actually a human-powered ornithopter. It was built in Canada by a team of students led by Todd Reichert. Todd is famous in the human-powered vehicle world. He holds more world records in human-powered vehicles than anybody. He won the Sikorsky Prize with a human-powered helicopter. He holds the record for the fastest speed in the human-powered land vehicle, bicycle. And he built this human-powered ornithopter. And it flapped its wings and sustained for about 150 yards. It was in level flight. It could not take off from level ground. It had to be towed up to altitude. But what you can't see in this picture, there are two cables that pull downward on the wings. And he's in there doing all kinds of motions with his shoulders and legs. And the wings are just bending like this. And it's sustained for 150 yards at reasonable efficiency. It could not climb. And I'm showing in the small picture above it. You probably can't make that out. But that is the Daedalus human-powered aircraft that flew 71 miles on 1/3 of a horsepower. So what I'm trying to show here is the difference between a human-powered ornithopter, the best one ever built, and the human-powered airplane with a propeller on the front, the best one ever built. The ornithopter takes 3 times the power and barely goes 150 yards. The airplane flew 71 miles at 1/3 of a horsepower. So clearly, we know how to build airplanes better than we know ornithopters. On the right is a model by Horst Rebiger. He built a series of models from probably a period of 20 years, and it's one of the most efficient ornithopters I could find on the web. There are videos of these things flying, not very long videos. It seems like most of his models didn't have much climb performance, or a wing would break, or he'd lose control of it, or he didn't have any of these videos where the thing would just fly away and start soaring or anything. But from what I could glean from his notes, a model like that needed about 200 watts to fly, whereas you could go out and just get a nice RC sailplane with a folding prop on front and sustain easily at 60 watts or less. Next. This is a picture of the Festo smart bird. So a lot of my friends know that I do ornithopters, and every 6 months someone sends me a video of the Festo smart bird, even though it first flew in 2011, because they think I've never seen this thing before. You've probably seen videos of it too. It really looks like a seagull. It's the same size as a seagull. The only thing is it weighs about 1/4 as much as a seagull weighs. It's like a seagull that's all hollowed out. And it has a very small motor. It actually has servos in the wing to twist the wing. So this wing does not necessarily deform due to the air loads. It's actually twisted by servos because they wanted to get the wing in just the right place. And you know how engineers are. Sometimes it's like if something has to move, put a motor on it. Well, nature doesn't do that. They use, flexible stuff to get that done usually. It weighed about 1 pound and had a 6.5-foot wingspan. That's, a 6.5-foot bird that only weighs 1 pound is pretty uncommon. There are some birds like that, but seagulls aren't one of them. They claimed high efficiency for this, but they had to do some hand waving on how efficient the motor and the gearbox was. And I've never seen any videos of this thing soaring. It does glide, but it's not, they mostly fly this thing indoors or in very light wind. But it's beautiful. I mean, it's beautifully built. It was funded by a large company. They probably spent, a significant fraction of $1 million creating this thing. Next. That is a picture of Otto Lilienthal, one of the first people to fly in an airplane. He flew mostly what we call hang gliders, but he wanted to build something that flapped its wings and flew, and that was one of his, and we envisioned this as maybe being a way to fly. People in the early days didn't understand how much power you needed. The human body wasn't capable of creating that level of power. But Otto Lilienthal was one of the first people to make documented flights, mainly in his gliders, and unfortunately died flying them. So I put his picture up there, but my goals are to build an efficient soaring aircraft that uses flapping wings for propulsion. I want to be able to climb nicely at reasonable efficiencies. I don't expect to get to propeller efficiency levels, but I also want to be able to soar. I don't want to be stuck with these floppy membrane wings that don't have airfoil shapes, which 90% of model ornithopters are like that. Very few of them have an actual airfoil. So, and I'm trying to make these wings deform automatically to minimize complexity and to mimic what happens in nature. Next. So let's just take a look at this video. We're going to go and play separately because it doesn't play through my presentation on this computer. So we're just going to jump over to a different screen here and fire it up. It says geese, slow, yeah, that one. This is a slow motion video of geese in flight. And what I just want you to see, look at the wing, how it's changing span. You see the wing extends and then the tip folds back and the outer panels were twisted heavily on the upstroke. In the upstroke, the outer panels are washed in. And then the wing looks almost flat, a little bit of washout on the downstroke. And we're so used to seeing this in movies and in nature that we don't, we just say, oh, that's how a bird flies. Well, there's probably a lot of reasons that it's doing that. That we have to keep that wing in a narrow angle of attack range and a narrow range of loading to be optimal. And it's all happening automatically right in front of us here. But none of these models really do this. And even the ones I'm going to show you today don't have all these degrees of freedom. The wings don't change span and fold up. Because a bird has feathers, it can change the area and span. The feathers just slide over each other and allow the wing to do that without having abrupt contour changes. My models have wings that have sort of more rigid skins. Let's go to the next slide. There we go. So here's what a bird wing looks like on the inside. Showing all these different degrees of freedom and some labels here for the hand wing is the outer part of the wing. That's where most of the interesting stuff happens. A lot of the twisting and folding actions happen out there. Showing the main flight feathers. All the feathers that cover the front of the wing have been removed in this drawing. This is a very lightweight, flexible structure. If any of you have ever picked up the wing of a dead bird, it weighs almost nothing compared to the body of the bird, where the muscles and all the ability to store energy and everything is. I mean, everything's at a premium on a bird. Weight is critical. Birds that migrate have to have the ability to store huge amounts of fat so that they can fly thousands of miles without stopping. They're just like airliners in that sense. There are birds that migrate 10,000 miles in a flight. Let's go to the next slide. All right, here's a bunch of vectors and stuff, and I'm going to just I'm not going to ask you to look closely at that or understand any of it, but the main mechanism of how a bird works is, let's just start with the downstroke. If you take the wing of one of your sailplanes and you were standing in the wind and you could hold it like at the root of the wing and just plunge it downward with like a 20-mile-an-hour wind blowing over it, you'd feel it pull forward. And the reason is, now I'm going to wave my hands here, they won't see this on the computer thing, but as you plunge the wing downward, the air is coming in. You know, if you had the wing sitting in this wind at an angle of attack, you start to move it downward, the air is coming in at a steeper and steeper angle. And as long as the wing doesn't stall, the lift vector on that wing is tilting more this way as you plunge it downward. You're developing a huge amount of suction on the wing. And you're doing work to do that. You're pushing down on the wing, that's work. The force times distance of doing that. So it doesn't come for free. You get this big forward force. If you ever have the opportunity to hold one of your wings, you actually don't even need to do it in wind. If you have to grab a wing, one of your half wings of your models, and stand in a big enough room, as you plunge it downward, let it rotate so it doesn't stall, and it'll just start pulling. You can feel this. It's how a propeller works. You know, the propeller blade is at a real steep angle moving downward, and there's all this thrust on the blade. It just keeps going round. So the downstroke is just like propeller mode. But you have to have enough lift during that motion to hold up the weight of the aircraft. Propellers don't do that unless you're a helicopter. Propellers are just pushing you forward or pulling you forward. The upstroke is trickier. On the upstroke, the question is, well, do you want lift on the wing while you go up? Do you want to go up so quickly that you actually make negative lift? You have to keep in mind that on an average up and down stroke, you have to hold up the weight of the airplane. So the average has to equal the weight. So if you pull negative lift on the upstroke, you need a lot more lift on the downstroke. And then there's the question of, well, what does that mean to the drag? Somewhere in there's an optimal way to move these wings, and people have calculated that. I'm going to show you that on the next slide. But the main thing is, I'll just tell you part of the answer right now. Part of the answer is you want lift. On everything except the outer tip, you want lift during the upstroke. That means, since the air is now coming in more this way, you're going to have to really angle that wing. Of course, the angle varies across the wing because the air is moving very fast at the tip when you do this and not so much in here. So you need a lot of twist on the upstroke. And then you're going to need less of it on the downstroke because the angle's steep from the flow. So that's why bird wings, when they're flapping, you see this, whoa, and then like that. So there's a big bias there towards being twisted like this on the upstroke. Let's go to the next slide. So people have calculated the optimal loading during the flapping cycle, and those gray lines are the tip vortices of the bird. If you were looking at the tip vortices of your glider or an air, you see contrails of an airliner, that's the condensation in the tip vortices. Condensation of moisture from the combustion of the engines collecting in the tip vortices. It's not chemtrails. So in a bird, it would look like this wavy pattern because on the downstroke, the whole wing is lifting and the tip vortexes shed right at the tip. But on the upstroke, part of the tip is lifting downward. And I won't get into all the aerodynamics, but if the lift is positive and then goes negative, you're going to get a big vortex right where the lift changes the most. That's where you get your vortex. So the effective span is decreased on the upstroke as the loading changes the way I just described. And you get this funny shape to the wake. That isn't the way all birds can fly. That's just the most efficient way to fly. And that defines what happens on the wing during the upstrokes and downstrokes. Next. This is another plot showing in the green is the span loading showing during the upstroke where the inboard part lifts up and the tip is lifting down, the downward part makes some thrust, the upward part makes almost zero thrust. And if you really look at what's happening in terms of the torque on the wing during the upstroke, it's just like there's almost like zero torque at the shoulder. It's just like the wing is just sort of just gently lifting itself up, and then the muscles really pull it hard down on the downstroke to get all that energy into the motion. Next. So can we build a model that comes close to achieving all this and glides well? Because I didn't tell you anything about how birds change the shape of the span and all that other stuff to achieve that shape, that response. So next one. So I did a bunch of analysis. I won't go into, once again, I won't bore you with all these details, but that's just a picture of an airfoil section that has mass and springiness and aerodynamic coefficients of lift, drag, and torque acting on it. And I threw that in a numerical optimizer for the entire stroke, and if we go to the next slide, I won't even ask you to read all that. It tells you like how the wing should be oriented during the up and down stroke. On this slide, the right side is kind of what the wing looks like during the downstroke. Looks a little washed out or angled slightly downward, and you can see a greater upward angle on the upstroke. This is for a very efficient cruising flight mode for this particular ornithopter. This just gives you an idea of what one wing section would look like. That's not the entire, that's just one airfoil on the wing, say 3/4 of the way out. Next. This is a model I built probably 10 years ago, and I tried to put together a whole bunch of pictures of one flapping stroke. This just had a foam wing. This was not an optimized model at all, but what I'm trying to show here, and it's going to be very hard to see with these tiny little pictures, but at the beginning of the upstroke, where there's a lot of acceleration, any mass behind the wing spar has inertia, and when this thing is pulling upward, that inertia just pulls the wing down way too much at the beginning of the upstroke. In the middle of the upstroke, it's not down as much. And then at the beginning of the downstroke, it's way up here. And in the middle of the downstroke, it's not nearly as twisted. That's not the way birds work. The maximum twist is always in the middle of the stroke. In the middle of the upstroke, it's twisted a lot, not at the beginning of the upstroke. Middle of the downstroke, it's twisted a lot, not at the beginning of the downstroke. So we're seeing a lot of response to this mass distribution, this extra weight way back here behind the spar, which you have feathers or a membrane, you don't have a lot of weight behind the spar. That's the reason you have to have such a lightweight wing structure on the back of a bird wing. You don't want this happening. This model wasn't built that way. It just had a slab of foam wing I cut out. So that didn't fly real well. So that's just an example of how you got to get the mass distribution and the flexibility right. Next. So let's just skip this. This is more things. This is a picture here trying to show what the wing should look like, but I kind of been waving my arms the whole time telling you that on the downstroke it looks, so in this drawing, the topmost thing shows a typical wing at 0 G. That means sitting there, like this model I brought today. See how the wings are washed in? You need that so that at 1 G flight, they're flat, like this. And then on the upstroke, they're twisted way in, and on the downstroke, they'll be twisted a little bit up. You need that bias and the twist in order to get the right shape throughout the stroke. The third drawing down is the downstroke, where everything is twisting appropriately across the wing. And then the last drawing is the upstroke, where the tips are twisted a lot, but the middle of the wing is still lifting. These are just hand drawings that are exaggerated. Next. Now, here's a bunch of ornithopters I built over the years. I'm just going to talk about 3 different ornithopters in detail, but I just want you to know I build, like every year or two, I build a few new ones and it's mainly been trying to figure out how to make a gearbox that won't break and then how to build a wing that works well. And I'm kind of zeroed in on it, I think. So next slide. We are going to also play this video off to the side because it won't play in the presentation. It's a compilation. So this is the ornithopter I presented here 4 years ago. This is sort of a summary video of it flying. And I thought, oh, this is a pretty good ornithopter back then. Now I don't think it's that good. It's got Dacron wings with aluminum wing ribs. It's built like a hang glider. But it's got ribs, it's got a carbon fiber spar. It's got these washout tubes near the tip that really wash in tubes. They hold the wing twisted down at 0 G. But you can see it's you don't see the fuselage undulating a lot. It's just cranking along. Now I'm going to reduce the flapping rate down to about 2 hertz. Here's 2.5 hertz, 150 watts. If you were to run that in really slow motion, you'll see kind of that nice twisting where the upstroke has a lot of wash-in on the outer tips, and there's just a little bit of wash-out on the downstroke, peaking in the middle of the stroke. And I can really slow the wings down here and just cruise around. Now this thing could glide, but the wing, it's a single surface wing. It doesn't have a defined leading edge. It's got just a single cambered surface. It's got a lot of drag. You can see that those tubes out towards the tip are trying to restrict the wing twist. But you can see the wing twist is kind of lumpy across the wing. For an ornithopter, this is considered a pretty good glide. But it's still kind of hard to catch a thermal with this thing. This is a little bit of onboard video. We'll just show a little bit of this. During climb out, it flaps pretty fast. Looks like it's beating itself to death. Because I just want to get it up a few hundred, like 100 feet or so. And then I slow it down. I don't want to play this too much because this video goes on for a while. I'll show you some more stuff that's more interesting. There's like the cruise flapping right there. So we'll go back to the presentation now. The rest of the video should play in line, so we won't have to jump out. Okay, next. So that thing weighed 5 pounds. Now, the latest Ornithopter is size and weight similar to that bird you see on the screen, although not nearly as beautiful or as efficient as a gannet. I've improved the airfoil because it's a full airfoiled wing. It's not just a single surface wing. I'll talk about that structure that I used. All of my ornithopters use a V-tail for pitch and yaw. They flap their wings with an average dihedral. So they're flapping, on average their wings look like this. And you can yaw them and get a dihedral effect and steer them like a 2-channel RC glider. I changed the flapping rate with the throttle. Real birds change the flapping amplitude more than the flapping rate. But changing amplitude is hard to do with a fixed gearbox setup. And all of them have a way to lock the wings for gliding. I use a mechanical lock with an Arduino microcontroller and a little Hall effect sensor to know when to stop the mechanism so that the mechanical lock will engage. Next slide. This is what I think my best ornithopter, I'll call it, I don't have a name for it. This is what it looks like. On the left it's gliding, and on the right that's the beginning of the downstroke. It's a robust, stable design. It's a platform for testing new wings and concepts. It's a fully profiled wing section with high torsional flexibility, passively deforming. This is almost 7.5 foot wingspan, weighs about 6 pounds. Wow. I have 2.5 hertz flapping rate, but I'm going to show you a video where I discovered that you can flap the wings extremely slowly on this thing and still sustain altitude. So let's go to the next slide. This is what the guts of it look like. On the right is the gearbox. I made this gearbox out of plywood and carbon and gears that I bought and a brushless motor. This is made not in a machine shop. This is made like on a model airplane workbench, with just basically a drill press and a jigsaw and a few other things. You can put ball bearings, flanged ball bearings into 1/8 inch plywood that has some carbon on it, put on there with epoxy, and the bearing will stay in place, and you can put shafts through it and mount a gear. You don't have to machine all this stuff. The cranks that it uses, I cut them out of aluminum on a bandsaw and drilled holes on them with a drill press. So there's no mill or lathe involved in making any of this. I've been using the same gearbox for over 5 or 6 years now. And that whole thing is a module that bolts into the fuselage of the Ornithopter. On the left side is a bit more interesting. I'm sorry the picture isn't better, but what you're looking down the wing spar. The wing spar is a set of carbon tubes. They change diameter depending on how flexible I want them. And you're seeing these struts that stick off the back. They're kind of like wing ribs. But what they do is they carry the torsion load of the skin into the spar. But you can see how it's zero load. There's 15 degrees of washing. Same idea that I've been saying all night is that you need this wings looking like this with no load, so that at 1G they're flat and flapping, they end up being more this way on the upstroke and then more this way on the downstroke. So you see that in the structure. That's the core structure of the wing. It's just a carbon tube, carbon ribs, and there's a diagonal spar that braces the thing fore and aft. And there's just some hinges for it. Next slide. This is sort of the big innovation since the last time I was there. If you look on the left, You see how my finger is holding up the surfaces of an airfoil wing skin? That's a skin that's cut numerically by a company called Flying Foam. I gave them the templates, and they cut that with a numerically controlled hot wire cutter to get, because it has to be cut precisely inside and out. And that's all cut out of 1 pound per cubic foot polystyrene foam, just beadboard foam, the crappy stuff, you know? That whole wing slides right onto the carbon structure you saw in the previous image. On the right-hand side, you see it all looks like an airfoil there. Well, how do I attach it? If I glue it down, it's not really going to twist well because it's glued everywhere. So what I did was I put strapping tape on the key areas where I wanted, where the ribs and spars were, and I got a big needle and thread, and I sewed the whole wings, the glove of the wing, onto the ribs and spars. It's all sewn on with just thread. The trailing edge of the wing, now if any of you have ever taken a tube and tried to twist it in torsion, it gets stiff. But if you slit the tube, it's real easy to twist. We need that slit so that the pieces of the tube can move past each other. The trailing edge of the wing is the place you do this on an airfoil. If you join the trailing edge, there's going to be stiffness from that, even from that foam. So the trailing edge is not glued. It's sewn together with thread so that on the trailing edge of the wing, those two upper and lower surfaces can move past each other. And that is what allows me to build what looks like a nice normal wing, but yet it twists like crazy and does all the things I want and weighs very little. Next slide. There's another. In this picture, you can actually see the wing, the tape that's on the wing, and where I've sewn the whole thing on. If you were to zoom in, you'd see that there's actual thread going through that tape. But what I'm really showing here is a spring. Unfortunately, that spring isn't connected to the anchor that it should be in this picture. But what I want to show you is that there's a spring that, what it does is when you lift the wings up, that spring is trying to pull the wings down. So that when you finally get all the way to the top of the upstroke, the springs are really pulling down on the wings. And that is because you need more power on the downstroke. And if you just hook a motor up to this thing, the motor's putting out roughly constant power. It's trying to run as fast as it can based on the load applied. So on the upstroke, it's going to drive your wings up way too fast. And on the downstroke, it's going to work way too hard. You can have the load on the motor is going to have huge oscillations between very low and very high. You put those springs on it, it evens everything out. You could say that I'm tuning the system for resonance, or you could just say I'm storing energy to even out the loads. But that spring is very important. It can improve the efficiency by a 40% reduction in power by just evening out things. So even this model I brought today, which I'll show you later, I have these bungees that I attach. They're not attached right now, but I use bungees from one wing to the other so that the motor is working against them on the upstroke and they're helping the downstroke. And in flight, the wings move smoothly, like that. Without the springs, it's like, you know, the upstroke is way too fast and the downstroke is way too slow. Ideally, I should have feedback control on the motor itself to hold the RPM, but that comes later. Next. It's a fancy chart. The one on the left is showing what birds do in terms of the flapping frequency versus the weight of the bird. Biologists like to make these charts on log scales showing how all birds obey a certain power law for scaling. All I'm doing is showing that I am building models that fall on the same scaling line as real birds. If you were to plot all the model airplane ornithopters built, most of them are not anywhere near this line. If they're real big, they're too light. If they're small, they flap too fast. You know, so I'm just saying that I am building a bird. You know, that's why my ornithopters, aside from the one I brought here today, tend to be big and heavy, not big and light. This airplane, there are some performance numbers here. The videos I'm about to show you are an airplane that has about 150. I didn't measure this exactly. 150 foot per minute sink rate at min sync, L over D of at least 10 to 1. I haven't really measured it, but I'm just eyeballing it. I've flown it with up to half a pound of extra junk on it, and it still climbs like crazy. It climbs at over 1,000 feet per minute. Let's go next. Let's play this video. It should play. So this is a flight showing a little bit of thermal soaring. I'll just hit it one more time, just let it go. Oops, go back.
Oh, yeah.
Yeah, just hit it once, it should start playing. Okay, see how the wings are washed in before I do anything with this? And then I open up the throttle and it'll just climb like crazy. Because I'm in a small park, I just want to get up and away from the trees. It's, you know, normally, you don't have to flap the wings that fast to fly. But even at what I consider a slightly high flapping rate, it doesn't look unnaturally fast. It looks a little bit fast, but not, you know, not crazy.
Is that the foam wing you showed earlier?
Yes, this is the fully profiled foam wing. So now I've kicked in the glide lock, and I also have to retrim it. There's a little bit of down trim that automatically happens. And then I just hook the thermal, and I just start circling, and you can see I'm higher already. And then I just kept going up, and I finally just flew out of it and said, okay, I had enough of that. Just want to land the thing. So it's hard to show in a video that you're thermaling, you know, except that the glider, you know, spins around a bunch of times and it doesn't appear to be coming down, or it just gets smaller. So I've done this many times with this aircraft. I'm just flying it in Sunnyvale, you know, in the afternoon on a typical day. It's not like I'm not going out in the desert and coring dust devils or anything. These are just typical thermals that you find around here. So here it's coming into land. You can see how flat the wing is. I'm flying really fast right there because I don't have any glide path control. I want to just burn off some altitude. But you can see that, you know, and now I'm almost stalling it right there. But you know, this thing has a reasonable glide ratio. You know, you can see the wings sort of collapse there from the springs. Next slide. So here's another video. This is, you know, those 360 cameras you can buy. So I put this. You can see the shadow of it on the wings. It's a ball-shaped camera, weighs about ½ a pound, and you can switch the view. So I made this video from on board the Ornithopter. You know, in slow motion, we might learn something from it, but I just, you know, sometimes people just want to see what's it like to be on the Ornithopter, and it's bumpy. You know, it's not perfectly smooth. You would not want to be in this airplane. But I mean, it's not the bumpiest Ornithopter I've ever built, but you know. And so here I am locking the wings for the glide. Look, you can see when we're gliding, if you look out towards the wingtip, maybe you'll see it again in the next shot. You can see the twist of the wing changing under load, even in glide, indicating just how flexible these wings are. In this case, you know, the glide is somewhat degraded with that giant ball sticking out on top. Okay, next. You can see the tape on the wing there. Here's just some sequence of the wing shape during the flapping cycle. Without going through each of these photos, one thing you'll notice is that the inner part of the wing isn't twisting much. And that's because there's a spar there. And that's a deficiency of this particular wing design. I would like the inboard part of the wing to twist more, to have kind of a shoulder joint action. That'll have to come later. So the tips of the wings are doing most of the work here. Next. And here's one more video. In this case, I was flying and my glide lock mechanism failed. I was trying to get the Ornithopter down. Oops, not playing. Hit it one more time. There we go. This is from a GoPro mounted on my head, so I couldn't zoom in. But if you look, you'll notice that I'm flapping really slowly, and occasionally I'm not flapping much at all. I'm just trying to get the thing to come down, and it won't come down. This slow, intermittent flapping is enough to sustain. Now, occasionally you'll see it flap really fast there because I stopped the wings with too much dihedral, it falls out of the sky. But you know, I flew around the park like this for several minutes, just saying, how am I going to get this thing down now that I can't lock the wings? And you know, there's where it falls, and I have to flap fast. But then I'm back to this, you know, really slow flapping. And the slow flapping, because of the high current involved, actually overheated the ESC 10 feet off the ground, and it did crash. But it was minor repairs. But I never tried to fly like that, and it's just an indication of the efficiency that just a few flaps and then glide, and a few more flaps and glide. This Ornithopter can do that. My gearbox isn't the right ratio for it, but it can fly like that. Next. So let me tell you about another Ornithopter I play with. This is the one I brought today. Turns out you can use servos, modern high-powered servos, to directly move the wings of an Ornithopter and make it fly. So I decided that this might be a way to do some other experiments with a lighter weight model that wasn't as you know, difficult to repair if it crashed as a 6-pound model. So I built a 6-foot span, 1.6 pound aircraft. Compared to the Festo Smart Bird, which is about the same size, this is still 60% heavier than a Festo Smart Bird. Let's go to the next slide. On the left, you see just a couple of big servos with some, the mounts for the servos have spars coming out of them. That's, you just put the wings right on the servos, basically.
Wow.
On the picture,
On the
picture on the right, you see that I filled in the structure so that it actually has pivots and ribs, and the ribs are at the correct wash-in. I'm using these MKS HV 777 servos. There's probably something better now. Before I go too much further with the servo discussion, let me just tell you, I would not recommend doing this because servos don't like being run back and forth all the time. You will wear the gearboxes out eventually. These servos cost like $200 each, and the nice thing is it allows you to program exactly how the wings move. The bad thing is that they're fragile, they eventually wear out, and it'd be better to just put a gearbox in it, and it would fly so much better with just one gearbox. The gearbox would weigh less than these two servos. Next. So here's two videos. Let's play the one on the left first. Okay, so this airplane is only 1.6 pounds, so it's more like a lightweight model airplane. It's like a floater, in terms of the glider world. It's got a single surface cambered airfoil, so it's not going to speed up much. And in this video, there is a little bit of lift over here. You can see it's kind of reacting to the lift, and I'm circling in it. And this airplane's thermal many times. It doesn't need much of a thermal to hold it up. But it also doesn't have much of a climb rate. You kind of need the help of lift if you want to get a few hundred feet in the air with this thing. Otherwise, it's just going to cruise around at about 20 or 30 feet of altitude most of the flight. So then, glide lock is just stopping the servos in the right place for this model. Unfortunately, there's a lot of current involved in holding the wings in that position. There's no mechanical lock here. And then, let's play the video on the right. So on the right, you'll see just on a day where there's no thermal activity, and I'm just cruising around, just to give you an idea of the nice, low flapping rate, and it's just kind of fun to take a model like this out and just fly it around yourself in the park, In both of these videos were when I only had one servo on each wing. I've since modified the model for 2 servos on each wing. It just made it heavier. It didn't really effectively add that much more power because the weight canceled out the power. It was not a cost-effective modification. This thing's, it's a very docile airplane. You just do whatever you want with it. So next slide. So for future work, this is a really bad drawing by hand that shows what I'm looking at now is what I think I'm just going to show you with motions on my body, but this slide is trying to tell you the same thing. Birds have a kind of a structure in their wings that look like this. And my models up till now don't have that. And I always wondered, why is it always like that? Oh, well, it allows it to fold. That's a kind of a nice thing about it. But it's important that the forearm have an angle to the main span of the wing, because the forearm twists like this, just like your forearm. It has 2 bones. It's torsionally kind of floppy. What you see, we've seen in the videos of the birds that when their wings are coming up, they pull them in like this. So in a bottom view, on the upstroke, the bird looks like this. It's pulling its wings up. If you draw a line off the forearm of the wing, and you look at all this lift on the wing during the upstroke, and in this case, the lift is negative out of the tip, like I was showing in the earlier charts. What it's doing is it gives you the axis of the structure is this way, and the forces are way behind. There's a big moment arm between this axis and where the lift acts. And that means the wing twists heavily on the upstroke automatically, simply because you created this angle here. Well, on the downstroke, you don't want as much twist. You want the wing to be effectively stiffer. So on the downstroke, the bird extends the span, which is also good for efficiency. Now, the loads are going to be roughly at the quarter chord of those airfoils, and the spar is here. There's not going to be much twisting. They're all in line. And on the downstroke, everything's stiff. On the upstroke, this makes it floppy. Stiff, floppy, stiff, floppy. And that's why I think birds do this, mostly. I haven't seen this in books anywhere, but I think that's kind of the key. So let's go to the next slide. Let's play this video. I modified this model with a set of wings that you do not see here today, where I put this flexible structure in here, and I put a string on it so that it's floppy on the upstroke and stiff on the downstroke. And just look at the motion. It looks a lot more bird-like. See, twisting like crazy on the upstroke, stiff on the downstroke. And it's just a short flight in the park. It's not clear whether the efficiency was improved or not. This model didn't just go climbing like crazy because it doesn't really have that much power. But it's a starting point for further investigation. And here it is in slow motion. You can sort of see that more natural looking twist of the wing as it goes by here. This needs a lot more optimization and analysis though. And I'm not sure how I'm going to pull this off as easily with my fully airfoiled wings. Because ideally I do want to change the span. I don't want to have a string hanging out that limits what the wing does on part of the motion versus the other part. Okay, I think that we're to the last slide, and then I'll just show you this model, and we'll be done. Let's go one more slide. So, just to summarize, very few efficient ornithopters have ever been built, especially very few have been built with fully passively twisting wings that are efficient. But yet we kind of know what the wings should do for efficiency. People have calculated it, they just haven't been able to build something that's lightweight and achieves the shape and the loadings that we need. And there's all these reasons why. There's inertial loads that are often neglected in the analysis and design process. And so engineers really have to put everything into the analysis and optimization to get this right. It's a good PhD topic, but not many people are doing it right. That's what the next few bullet points talk about. What I feel I've done is create a successful test bed to a platform that serves as a test bed to test these ideas. And I've been able to demonstrate reasonable flapping efficiency and a reasonably decent lift-to-drag ratio so that I can finally soar these things rather than just watch them fall out of the sky like a brick. So to finish up, I'm just going to show you how this ornithopter that I brought, this is the one with the servos in the wing. I just want to show you the wings moving. It's not that exciting. But, so you turn it on, servos make a lot of noise. They're holding up the weight of the wings here. Get this out of there. And just pull the throttle stick back and the wings are in glide position. I'm going to advance the throttle and you get, this particular one, the amplitude and the frequency changes with throttle. So here's some blown stuff. And that's just the servos. That's enough to fly it there. See the wings deforming, and you stop it and it's ready to glide. It just has the two channels here. If the batteries die, you're in deep trouble, because if you're flying, the wings can do this. This is one of the hidden secrets that only ornithopter builders know, is that when things go wrong, you have the worst crashes with an ornithopter, because typically you lose an entire wing. It either breaks off or the mechanism fails, and you hit the ground with wings like this. And that's why if you look closely at this model, you see all these repairs and whatever. Anyway, that's all I have. I'd be happy to answer any questions if you have any, if we have time.
Gary, maybe let's ask the audience first. Gary, any questions from your side?
Yeah, I'll ask one. Kyle, fantastic presentation. I appreciate you bringing this in. Good question. Have you flown with birds, and what do birds think of your machine?
That's a really good question, because birds are attracted to these things and they tend to go crazy. I don't know what the response is. I don't know if they think it's a wounded bird or what, but it's almost inevitable that if I fly an ornithopter, a seagull or some other large bird is going to come from out of nowhere and start interacting with it. Like, they don't attack it, but they start circling it and making noises. This happens a lot. And you'll see this in a lot of YouTube videos where people are flying ornithopters, that other birds will just flock from out of nowhere. I don't know if they think it's a predator or if they think it's in trouble. I've never figured it out. That's why I also like the glide capability, because if I'm soaring, then they tend to ignore it more. But as soon as it starts flapping, they get very excited about it.
Excellent, thank you. Anyone else online with a question? You can unmute, just ask the question.
What size battery do you have in it?
Oh, and this one?
Yeah.
This is just...
Maybe repeat the question.
Oh, so the question is, what size battery is in this Ornithopter that I just showed the wings flapping? This is, to keep the weight light, I have just a 910 milliamp hour 2S battery. It's a tiny battery. I can fly for, just out in the park, flying the thing, I don't know, maybe 10 or 15 minutes of just, maybe not 10, let's just say 5 to 10 minutes of flapping with that battery. But the whole battery pack is very small and light. This thing is, other people have built servo flap ornithopters, but they don't put a full fuselage on it, and they don't use these kind of wings. They make them much lighter so they climb better. They look more like those membrane ornithopters I showed at the beginning. This one is kind of right at the limit of what can climb with a servo flap system. And I should mention, the whole thing is controlled by a little Arduino microcontroller. And I have build threads on RC Group, and the source code is all there if you wanted to try one of these things. I'm not recommending you do it with servos. But there's a little microcontroller, so when I move the throttle, the servos are going like with a sine wave, which isn't a normal thing that you get from your RC transmitter. Yeah.
Two questions. First one, how does the wing loading on this model compare to something like the Gannet, which you said it was basically similar in size?
Oh, so the Gannet is more like the heavier Ornithopter I built. This is a lightweight one, so this is a lower wing loading. The Gannet is a little bit higher wing loading than my large Ornithopter, but they are similar. Gannet is a seabird. Seabirds tend to have very high wing loadings. They tend to do a lot of dynamic soaring, which, my models aren't. It's funny, my bigger model is probably more eagle-like in span and wing loading. I probably should have compared it to that more than the Gannet.
Okay, the second question, let's see the standard surfaces, VTail and all of that, but do birds, when they're executing turns, do they use their wings as ailerons as?
Yep, all exclusively. I mean, everything's done through the wings. The birds, they do differentially twist, they can asymmetrically change span, they can shift their wings fore and aft. It's almost like weight shift for pitch. There have been many experiments where they trim all the tail feathers off of a bird and it still flies reasonably well. They don't absolutely need the tail feathers to fly. So birds are true, actively stabilized flying wing aircraft. And they do have the ability to just like your forearm has muscles, birds in the hand, the wrist and hand area, and in the forearm can do twist. So yeah, they have to do that. We've all seen birds, gale force winds, they're out there still flying, and they can just twist the whole wing panel. Maybe you've seen videos where they put the camera on the eagle. Huge amount of motion that the wings go through, just in soaring flight even.
Thank you.
Yeah. Yes.
You mentioned a little bit between amplitude and flapping frequency, but what is that relationship? Is a faster better or more movement better, and where is the best efficiency, sort of around the centers?
So there's this dimensionless parameter called the Struhal number, S-T-R-O-U-H-A-L, Struhal number. It involves the amplitude and frequency of flapping. And what it really is, it's an indication of the angle that the air makes to the wing at maximum downward motion, like in the middle of the flapping stroke. It tells you just how much angle you're generating. And what you find is for almost every bird except the hovering birds, the Struhal number, from the biggest to the smallest bird, is in this narrow range of I forget what it is, it's a dimensionless number, it's a number like 2. So they all have a Struhal number of 2. And that means that the amplitude and frequencies can trade off against each other versus the flight speed in such a way that this angle never gets ridiculously steep. And that makes sense because that's when you're going to stall the thing, So these birds are flying such that in general the angles are changing a small amount. And if you see the models that you buy in the toy store with the membrane wings, you can just see from how ridiculously large amount of twist these models need just to fly at any speed, that they're way off the mark in screw hole number. Whereas my models do twist a lot during climb, but when you put them close to that slow flapping cruise, the screw hole numbers are very close to what real birds have.
So I'm curious, what kind of educational background do you have, and does this relate to your day job, or how's that connected? You seem to know a lot about
Well,
it.
I have a doctorate in aeronautical engineering, and I've been building model airplanes since I was 3, so I'm young, dyed in the wool like most of the people here. And I used to have a business manufacturing drones for about 20 years. We were building drones in 1999, not like people do, with gas engine powered things. But now I work in the medical device field now, and I still do airplanes. I mean, I'm going to be building model airplanes forever, but this is like research for fun. So yeah, I have a background in all this stuff, but I'm not doing research level work. This isn't like I'm trying to do a thesis on it or anything, and I'm not writing any technical papers on it. Although it's possible that there's enough work here that would make a technical paper. But the main thing is to have working examples of things. I mean, we all know that you hear all the theories and stuff, but if you can't build it and demonstrate it, I mean, did it really make any sense? In the end, it has to just be something that you can show to people or that they can duplicate themselves. And that's what I'm trying to do here, is to say, look, I think this is the way a bird works. This is the way I think you should build an ornithopter, and then I go and build one and see if it works. And it's just a very basic design cycle.
Any other questions? Any more questions from you, Gary, and the gang?
Yeah, there's one from Alex online here. He says in the chat box, in nature, are there any prominent rotary joints that are used with something that resembles a propeller?
There have been recent discoveries of rotary joints in nature, but the ones that I know of are mostly like a single-cell organism living inside another single-cell organism and spinning around to propel it. So that's at a completely different Reynolds number and scale. But there are technically some rotary joints. There are even pictures, X-ray pictures, of the equivalent of a gear, 2 meshing gears inside of an animal made out of bone. But it's a good point that, in the mechanical world, it's easy for us to make continuously rotating things because we don't have to have blood vessels and nerves going across these joints. You can just have the propeller spinning. You don't have to supply it with all the things that a living organism needs. Living organisms, they need blood vessels, nerves, all that kind of stuff moving across these boundaries. And therefore, you don't see continuously rotating things. Animals don't have wheels. We have legs. Birds don't have propellers. They have flapping, reciprocating wings. So animal locomotion is dominated by reciprocating motion because of these biological constraints. But there are a few niche exceptions.
One question? Yeah.
All your flapping, is that in a single axis, or is there any work in multi-axis?
On this one, it's all single. It's just there's this one hinge axis,
Yeah, but
and it flies a little nose up, so it's kind of.
the birds use a multi-axis type thing, so do they?
Well, they do. I was talking about how they change the span in the plane here of the wing, and there's probably some rotation in the shoulder joint. You could call all that multi-axis, but it is still primarily the wing panel moving like this, and then the wing, and then in and out for these other degrees of freedom that affect twist and the shape of the wing. But it's like if I were doing this as a thesis, I would write a big dynamic simulation. I'd put in those degrees of freedom, a decent aerodynamics model, a structure model with all the inertia and flexibility, and I'd throw an optimizer at it and say, give me the least power for cyclic motion that supports the weight of the vehicle and moves it at a certain speed with the least power. And I'd look at those solutions, and I would let the optimizer change the structure and things associated with the degrees of freedom to achieve it so that I know I could build it. A lot of people have done that kind of work, but they prescribe the motion of the wing. They don't know how they're going to get it. They just say, I'm going to make the wing move like this, and I'm going to see if it's more efficient. Well, that's great. What do you do, put a motor out there? Birds don't have big motors out in their wings. So you really need the wing itself to change shape during these motions with muscles at specific reasonable locations, and then see how to make that thing as efficient as possible without falling out of the sky. And that's a lot of work. It's actually easier for me to just build models and test at the moment, but it would be nice to couple it with the analysis.
Okay, so one last question.
One last one. I'm curious to know how you control the amount of twist in the ribs up and down. Is that controlled by
No.
the shape of the fabric on
Oh,
top?
well, yeah, this is what I call the passive part. It's all, the loading determines how much this deforms. So you see, if it's loaded, it's, because there is kind of a membrane quality, it tends to get stiffer and stiffer as you deflect it more and more, so it's sort of self-limiting. But for the most part, it's, this is a tube that is made of carbon, and it doesn't want to twist, but it does twist a bit, because I've made it small enough that these loads can twist it. So I've chosen this to be, eyeballed it to be appropriate for this kind of an application, so that it'll be a good shape for gliding, nominally low twist wing for gliding, and then it'll have that characteristic that on the downstroke we got a bit of washout, and on the upstroke we got a lot of wash in. That's why the whole thing's biased like that when there's no load on it. So, and you can see as I do this here, you can see it sort of, I don't know, I can see it because my eyeballs are close to it. I don't know if you can see how it's more on the up, it's twisted than it is on the down. But it's all just happening from the structure. So there's no servo making that happen, there's no cables. It's just the way the wing is built.
All right, thank you, Steve.
No, you could
Thank
hook
you,
that
sounds
up
great.
to
Okay, we'll talk to you later.
Okay, thanks again for the